started. Thanks a lot for having me here. So this is what I'm going to talk about. It's not good.
Is it better? Oh yeah, it's better. Alright, so this is what I'm going to talk about. As mentioned, my background is not on Hadoop or not on data at all. I've been working on machine learning data mining before I switched to data here. And that means that I have to learn a lot. That also means that I have to have lots of interesting discussions, and also that I have somewhat often a different perspective of things than many of the people who have been around longer. So the talk is going to be about a little bit about what I learned and the way I see things with Hadoop, and also the second part maybe some of the things where I was surprised to see that some of the things I thought were a natural fit from my background aren't as common as I thought they would be in Hadoop. So for instance, I know that little trick that sometimes can reduce runtimes by 99% or more. So maybe that's something like that could be useful to some of you, I hope. Alright, so let's get started with what I think is great about Hadoop, and also what I think about what's important about Hadoop. So I've had tons of discussions about Hadoop, and one of the reasons for that is that NVIDIA just released a new Hadoop Summit, and NVIDIA just had released a latest version, and we have a personal edition that runs on one desktop, and it even has a limit of the data it can run. So that's definitely not big data. So we have tons of people who came over and said, oh, that's crazy. That's not how you're supposed to use it. What is that about? So I talked a lot about what is Hadoop about. And to me, there's a lot. I mean, it's a whole ecosystem. There's a lot that is part of Hadoop. But there are two things that stand out. The first one is if you have big data, then chances are that something will break down eventually. So you have to have failure tolerance. And the solution is redundant storage, HDFS. And then the other big part is resource utilization. If you have tons of data, then you need tons of gear to process all the data. So that means you better make sure that you use the resources efficiently. And to me, that's something that is universally important. That's not something that's only important for big data. I think that's something that also is important on my notebook. You know, I don't want to lose stuff on my notebook too. I have backup too, so I have redundancy too. The difference is with Hadoop you have stable when you get redundancy. So what I learned is that most of the stuff that is important in Hadoop is universally important. And I thought in particular that sequential data access is something that's underrated. That's something that's not everybody agrees on that. So I stumbled across that paper a while ago. I love the title. Nobody ever got fired for using Hadoop in a cluster. That's good to know. Top security is the word nowadays. But if you read the paper, it claims that the price for RAM goes down so radically, so quickly, that nowadays it's maybe a better idea to scale by putting more RAM in a single machine than by adding nodes to a Hadoop cluster. So there's lots of stuff you can argue about that. It's not a bad paper. But my point, one of the things I think that the authors are missing here is the fact that even if you get rid of the hard disks, even if you just work with memory, most of the principles, most of the stuff that Hadoop is about still hold true. In particular, even the sequential access part holds true. It is true that Hadoop has started or to make sure that there is sequential data access, because on hard disks, the difference between random and sequential access is the reverse. So it's 5 orders of magnitude that you gain by having sequential access. But even if you switch to SSD or DRAM, you still have quite a tremendous speed up by using sequential data access. So that's one of the things I learned, and that's one of the things that aren't really reported a lot when you look, at least if you look at the popular stuff on YouTube. I was even told it's getting worse. So if you look at the with the DRAM, with the RAM technology, it goes to currently, if that prediction holds true, then the latest DDR4 RAM people are working on right now, it has up to 4 times the latency than the DDR RAM from last year. So it's getting worse and random. So that means to me that regardless of whether it's called Hadoop or not, regardless of whether you're running on memory or on hard disk, you better, if you want to get efficiency and performance, you better make sure that you access the data sequentially. I think that's one of the big take-home messages for me. And of course, if you're trying to solve a problem, usually you don't care about, you don't mind whether you should be sequential or random. You really want to get a problem solved. And so how can you make sure, or how can you design your algorithms that they access the data sequentially and make use of that data? So one way to look at that, one way I found helpful often, is to sit down and look at the roadblocks. The roadblocks that, so whenever you have to stop because you can't just code, because you figure out that there's something that takes longer, or something that I can't solve by just writing lines of code. And very often, these analytics, that's where I work, there's two types of roadblocks. There's definitely way more, but that's the ones that I have encountered. The first one I call needle in a haystack. That's when, in order to solve that problem, I need to have access to that particular piece of information, and that's in somewhere and I don't have access to it right now. So the good news is that on a very high level, you know how to solve these kind of problems. We just sort the data, right? If you have a haystack, you just sort all the hay by size, for instance, and then you look just for these that have the same size as the needle. And the other good news is that there's lots of good technology to address that problem. There's another roadblock that I encounter a lot, and that is you can do something. Say, in order to finish a task, you have to look at billions and trillions of data points. You have to crunch all of the numbers. So that's something where I have a feeling, so that's where the Hadoop people usually say the solution to that is utilization, and you better just use for that. And my perspective on that is that one can do better. So I don't think that's the best possible way to solve that problem. And for the rest of the talk, I'd like to focus on that a bit, and instead of explaining what I want to do, what I think so, let me just introduce a small example. So here's the example. It's a simple task. Imagine you're looking at a web company. They have a web page, and first they have a box, and they keep a table of all the customers they have and the links they click on. So they know that 50 customers click on link A, link B, and so on. And then, of course, some of the customers buy stuff. So you also have a second table where you have the item the customer bought and the price paid for that. So now some marketing guy has to use as maybe there is some correlation between the two. Maybe you can figure out people who click on link A on average pay more money. So that would be great to know. Can we generate a table that tells us if someone has clicked on link A, average pays that particular price, and if you have clicked on link B, then average is clicked on the other price. So that's an easy job. I guess everybody of you know how to do that. So the easiest solution is if you have something like Hive or Pig installed, you just go there, you enter your query, and then Hive does all the hardware in the backend. So you create two MapReduce jobs. The first one to join the two tables, and the second one to do the group by and the averaging, and then a few hours later you can solve it. Now, if that's something you need to do more than once, and if that's something that you should be done as quickly as possible, you can sit down and try to make it faster. And one way to do that is to just, so probably all of you guys know how to do that. You just sit down and look at the code, and you see that you actually don't need two MapReduce jobs. One is enough, so you could just have two members that put the customer ID, the key, and then the information in the value, and then reduce it, you get all the data exactly in the right order. So you can average over a single customer first, and then step-by-step average over all the customers. So that's straightforward too. But now what happens if your marketing guy says, I need it faster? How can you make it faster? And that's the point where usually if you talk to people, if you walk around at a summit, people will tell you, yeah, you can throw more hardware in, you can have more than one use and so on. Sometimes you know the data is already pre-sorted, so then you don't need to use it, you can just go to the matter. But is there anything else? How else do you get this thing to go faster? And that's usually the point where I, sitting in the audience and talking about it, so get a little bit nervous because to me there's a really obvious way to make it faster that nobody keeps on talking about. And this is I think what you can do. I guess the first thing you can do is just add one single line of code. And that code just takes the current average. So remember, it will usually keep the average of the data points you see in the file. You just keep the current value you have, and you output that and show that to the user. And then what you get is usually something like that. So this is on the x-axis, it's the number of iterations, and on the y-axis you have the current average. So what you usually get is you get the very first few iterations, you get a little bit of fluctuation, but after a while, the whole thing is just flat. So that means the average just doesn't change anymore, right? So the obvious solution is just stop loading. Just don't have it run all the time, just stop. Right, so that sounds like great, but that sounds like great advice that works good in the demo, but never works in practice. So the fundamental question here is, it's nice that that works on my particular data set, but is it something that works with principle and all kinds of data, specifically real data I have? And, or to ask the question in a better way, under which conditions does that trick work? And it turns out that lots of people have been asking the kind of question, and some people have been answering it. They're usually called statisticians. So the answer is this: yes, that trick works all the time with the two conditions. And the two conditions are this. The first condition is the data has to be ordered randomly. The problem, if the data is ordered randomly, is this. Let's assume the data is ordered maybe over time. So what could happen is that the things just change over time. So there could be, initially there could be a boom, so people spend tons of money, but then there's a bust, people don't spend a lot of money. So if you stop early, you don't see the later data points, so that's why you're estimating wrong. That's one of the things that can happen. Fortunately, getting the data in random order is easy, right? Everybody knows how to do that. The second condition that needs to be met is the distribution of the values you get must be somewhat well behaved. So what does well behaved mean? Let me give you an example of a not so well behaved distribution. Let's assume that most of the people just spend between $0 and $10 on the items to sell. But there's one really crazy guy who clearly has way too much money and he decides to spend $1 million on one item. Right? So if you have a case like that, and if you start doing the average, then the average stays between 0 and 10 for most of the time until you see that crazy guy and then it goes up like that. So that means you can never slow down because there's always a chance that you might have that crazy guy and he will kill your estimate. Right? So that's what I mean with being well behaved. So basically, I want that the distribution doesn't have any extreme levels. So there's some different ways to write it out formally, and these statisticians have done that. I guess probably the easiest way to formalize well behavedness is to just assume that all the values are between 0 and 10 levels, and there aren't any big outliers. If you have outliers, you can remove them in the first place. So if these conditions are met, then you can go to the statistical curve, and you'll find, for instance, stuff like that. Inequality over there, it pretty much tells you that you can argue, you can quantify how good your estimate is. So for instance, you could say, if I have xi to xn numbers, total numbers, and I just take the average for the first certain many, then the probability that that estimate is wrong by a certain threshold is smaller than that term here on the right. And I'm not going to go into details, but the interesting part here is that that's something that is exponential decay. So what that thing essentially says is that you get no guarantee whatsoever for the first part, for the first few iterations, but then after a certain threshold, the probability that you're wrong goes down exponentially. And that's good to know. So if you plot the numbers in that equation, then you get something like if all the prices in the database are between 0 and $10, and we stop after seeing 10 million out of the 1 billion records, then the estimate has a 0.000 and so on chance of being wrong by more than 1 cent. So that's a speed up of 99%. Right? So that's you save, you're just taking 100 of all the information. So should we be concerned about that chance of being wrong? According to the key table of unlikely events, it's 500 times as likely as getting struck by lightning. So that means I'm not really concerned about it. Alright, so that's great. That's great if you deal with averages, but of course, most of the stuff people work on is more complicated than that, right? You sometimes have average counts, and then you there's, I guess, one of the most helpful, I thought, results are results on mappings and functions. For instance, if you don't have just 2 links on a website, like let's say 1,000 links, and you're not interested in finding the other future one, you just want to find the best one that predicts the highest price customer paid. So you have results on that. So that's good news. The bad news is most of these results are not comprehensible to humans. So it's mostly lots of formulas, lots of math stuff that you don't want to read. So that's why I find myself often ignoring the actual formulas, the actual math of it. To me, it's better to just understand what the principle behind that is. And most of these results you should get just basically tell you that if you know more about the global behaviors of the distribution, then that means you can solve earlier. For instance, in our example, I have the assumption that I know that all values are between $0 and $10. If now somebody comes up and tells me, you know what, I also happen to know the standard deviation of all these numbers, and it's value X, that means that I can still know the 10 or maybe only have 1 million data points. And then also if somebody else tells me, you know what, I happen to know that it's distributed normally, so that you probably can start at 1,000 data points. Right? So that's pretty much the only thing that these results tell you. And in practice, most of the data is well better behaved than these results will tell you. So conversions is usually very fast in practice. So the way that I look at that is I usually have a rule of thumb that tells me whether or not it's a good idea to use these estimation techniques. And the rule of thumb goes like that. Sit down, think about the problem. What happens if you have the ability to change one data point, one record in your data in the table? Does that totally mess up the result, or would that just barely change anything in the result? So if that has this ability, that change could mess up the result, then estimation will work. If it barely changes anything, then estimation goes like it's on. That's usually what it is. So that's the rule of thumb I use. And I guess the bigger problem for applying these kind of techniques is not actually using them. The bigger problem is explaining to your customer, explaining to your boss what's happening. Because these people don't know anything about probabilities and they don't care, they're afraid of getting stuff right. So the way I explain it usually is I don't talk about probabilities, I mostly talk about the trade-off between accuracy and runtime. So what you can do is you can just start your job, and then give estimates every 2 minutes to the user. So if the user gets a few fluctuations first after 5 minutes, and then he gets all the same value for the next 2 hours, then he will stop the run on his own. Yeah? You don't have to tell him, you will do it on his own. So these kind of algorithms that just give feedback all the time, and just get better accuracy. There's a name for these kind of algorithms, and they're called anytime algorithms. If you think that's helpful for you, Google for it. There's not a lot, but there's some research on it. I think that's one of the things that should be built into Compute. I think it's kind of a perfect match, but I don't see a lot, at least at the places I go to. So that's one thing. And then the other thing is if you have that concept of not having to work with the actual data, but working with estimates, back of your head, then sometimes it influences the way you write your algorithms. So here's an example about that. So this is about clustering data mining. That's the stuff I know most about, so that's why I took that example. But I'm sure there are tons of other applications where you can use this or a similar technique. So for clustering, most of you probably know what clustering is. The idea of clustering is you have a bunch of data points, and you like to partition that into clusters, that is subsets where the instances in one set are similar to each other, but dissimilar to all the others. So that's, we try to find subgroups that are similar with regard to each other, but dissimilar to the others. That's what clustering does. And if you look at the textbook solution for that, you usually find the first algorithm that you find is called techniques. And the good news is techniques is available as part of Yahoo for Hadoop. So you can go and run it on Hadoop just by downloading Hadoop. And the way it's implemented is exactly the way it is written down in the textbook. So what it does is it pulls the first clustering out of thin air, then it gets that on the data, then it sees, okay, it's not the best one, it improves that, that's the reuser, and then it starts, it iterates, it starts a new memory, and again, it evaluates the current cluster, and then it improves it. So that's the textbook way of doing things. But now, you can't sit down, lean back, and think about what happens if I'm able to change one data point in my database. Does that really change the clustering? Does that change the clustering dramatically? The answer is it should. If that changes the clustering, then you probably have a data set where you shouldn't cluster in the first place. So that means you don't have to work all the data, you can work estimates. And that means you can also write your algorithm in a different way. For instance, what you can do is, instead of doing all these iterations, you can just take your data, split it randomly in a set of different samples, and then use parallel processing to do your clustering on each of these samples, and send the results back to the user. So what the user will get is will get all kinds of clusters, and you will get, so you will see if all of them send back the same clustering all the time, then you know, okay, that's not going to change. If I add more processing, that's not going to change anything. Right? So I found a robust kind of clustering there. If you get all kinds of clusters that disagree with each other, then that's probably a sign that there isn't really a good clustering in there, and that you probably shouldn't take too much attention to whatever is coming out of it. So what you get is you not only get a cluster, you also get some estimate about the robustness of the cluster, which is important information. Right? So that works well for clustering. It also works very well for sort of predictive analytics. There are Terra feature, a lot of the large-scale machine learning stuff works in this kind of way, and also a lot of machine learning stuff actually is just optimization. So it solves problems. What is the best A that maximizes some B? So a lot of problems to care about can be express optimization problems. So this approach, a lot of the time, works well for these kind of problems. So I think that's something that should be that's relevant in practice, I think. But I haven't seen that a lot in Hadoop. So yeah, I guess I'm running out of time. That's pretty much what I was trying to talk about. So here's just a summary. So I guess to me, since I've come from that background, one of the things that are maybe at least underappreciated a bit, one of the things that are very likely is the fact that sequential access is a great way to crunch numbers efficiently to make use of all of these sources. It works specifically well for all kinds of number crunching that has any sort of aggregation in there. But what's been missing, I think, is the fact that you can speed up things tremendously if you use the fact that randomness allows you to grab estimates of the samples that involve the data. And I think it would be great if you could have some more support for that. And also, I think it's something that we should know. But that's it.